Okay, great. Uh, Hi, everyone. Welcome to another APS GPC seminar. It's my pleasure to introduce today's speaker, Professor Geoff Vallis. Geoff is a professor of mathematics at the University of Exeter. Until recently, he was in fact the chair of the department. Before Exeter, he was at Princeton and UC Santa Cruz. Geoff is a physicist by training. He has an undergrad degree and a PhD in physics from Imperial College and Oxford. And Geoff has done pioneering work on geophysical turbulence, GFD, and climate dynamics, both on atmospheric and ocean. And in fact, last year, he was elected as a fellow of American Physical Society to a nomination from the GPC unit. Geoff has written a number of very popular books, including one of the major textbooks on atmospheric and oceanic fluid dynamics, as well as a book more for like a general audience. So if you are a mathematician or physicist or an engineer who is interested in learning more about climate science and maybe entering this field, Geoff has a great book from Princeton Press that you can read. That's the book that actually I read when I decided to become a climate scientist. So Geoff is a great author, both for research papers and for books, and he gives great presentations. So we are very happy that he's here today to tell us about planetary climates and paleoclimates. These are topics that are very interesting, but I don't think we had a speaker before who talked about this. So before moving forward with Geoff's talk, I just want to say that if you have any question, please put the questions, ask them through the Q&A features, and Geoff will answer them at the end. So without any further ado, Geoff, the floor is yours.
Thank you, Pedram. I'll go to full screen. Hopefully you can see a full screen now.
Looks good.
Good. All right, well, it's really nice to be here, even though I'm actually in my office. Although Pedram said I'm based at the University of Exeter, I'm currently at UC Santa Cruz, which was where actually I had my first faculty job. I'm here for the year on sabbatical. So what I'm going to do today is talk about two topics which I think are just different sides of the same coin, namely planetary climate and paleoclimates, both a little bit different from how we study today's climate, I think. And I want to mention this work has been done over the years, starting with Jonathan Mitchell 10, 15 years ago, Sam Potter, James Penn, Matthew Henry, and Quentin Nicolas, who's a student with me last summer, actually, at the GFD program. Had many conversations and input from my colleagues at Exeter and at GFDL. Okay. I don't want to go forward. Let's try this. Okay, technical problem to begin with. Okay, good. Okay, this is a slightly old slide, but it's how we conventionally study climate, one of the ways that we study climate using general circulation models. That's the most powerful tool we have to study weather and climate. And what you see here is a globe covered in a grid. We use that grid to solve the fluid dynamics equations. And at each location, at each grid point, we have various what are commonly known as physical parameterizations, radiation, evaporation, condensation, rainfall, and so on. And what has happened over the past years is there's a tendency, a natural tendency, to make these models as complete as possible. And upshot of that is that the models are complicated and hard to understand. So let's just show you a slide showing the evolution of climate models over the years, starting with the 1960s, back to the work of Manabe and his colleagues. Mainly just models just had the atmosphere, land surface, and the ocean. 70s and 80s added sea ice. In the 90s, aerosol processes to get the clouds right, some volcanic processes. 2000s, even more complicated. People started adding the carbon cycle, dust, sea spray, vegetation. And since then, GCMs have become known as Earth system models, and they have biogeochemical cycles and ice sheets and so on. And well, the issue, of course, is, I mean, if you can imagine a map, if you can imagine a model being analogous to a map of some region, and eventually, as the map becomes more complete, it becomes the same size as the actual surface of the Earth, becomes as complete as the surface of the Earth, and that's, in a sense, where aspects of simulation have gone, and that's become known as the digital twin. And again, for some reason, I'm having trouble advancing, but a digital twin is essentially a computer model that attempts to be indistinguishable from the real system to all intents and purposes. It uses the natural laws where possible, which is a simulation. It also uses machine learning, artificial intelligence techniques, and incorporates data in real time where possible. Here's a couple of definitions, one from IBM. A digital twin is a virtual representation of an object or system that spans its life cycle. It's updated from real-time data, uses simulation, machine learning, and reasoning to help decision making. Wikipedia says it's a digital model of an intended or actual real-world physical product that serves as the effectively indistinguishable digital counterpart of it for practical purposes. There's no mention of understanding in either of these, and perhaps to some degree it's not needed because the digital twin is doing the simulation for you, and arguably there is no need for understanding if you can actually simulate what's going on. So ECMWF, one of the leading weather forecast models in the world, has gone down the route of digital twins. They say the digital twin will support the analysis and testing of scenarios, support sustainable development, etc., etc. It will integrate sea, atmospheric, land, and hydrology, and so on. And recently that has been taken to one step beyond that, which is to actually forget about the physical laws. And one group to do that comes from Huawei, the technology company, have a product called Pangu Weather, which has an AI-based weather forecasting system that produces stronger deterministic forecasts than the conventional model, the ECMWF model, does on all tested weather variables. And just yesterday, the following headline popped up in the Financial Times, based on a paper published in Science earlier this week by Lam et al., coming from Google DeepMind. The headline is that AI outperforms conventional weather forecasts for the first time. Of course, that's not without, well, just one historical note, in the sense that Ed Lorenz, one of the founders of chaos theory, tried something rather similar way back in 1969 by doing analog forecasting. So he looked at analogs of past weather, and he wanted to see how close they matched the actual forecast of today's weather as a possible way of forecasting. didn't do all that well, but he didn't have available to him all of the data that's available now. And in a sense, weather forecasting is a natural way to proceed for AI, because what AI does well, and for example, natural models look to do is natural language models look to see what word most likely fits after the previous word. In weather forecasting, you'll look to see what weather state proceeds most naturally from the previous weather state. So it's well suited for AI methods. With some caveats, Simon Voss, leading scientist at the UK Met Office, asks the pertinent question: it's fair to ask whether AI-based systems are able to pick up new extremes if these systems have only been trained on previous weather conditions. And that brings up the question of data. Now, in present-day Earth, or looking back over the historical record of, say, the last 50 years, when we've had lots of data from satellites and radiosondes and so on. So observations, which are often massaged and become reanalyses or state estimates, and they're put onto a grid. And if you have a grid, this is what Pangu Weather used, of 1/4 of a degree global, 50 vertical levels, hourly, 50 years, lots of fields, velocity, temperature, humidity, and so on. That comes up to about 60 terabytes of data. And that's vastly more than we have for other planets and for paleoclimates. So if we look just at solar system planets, we have cloud level observations, which we can get from telescopes or from missions. We have occasional probes which drop down into the atmosphere. In particular, that has been done for Venus, Mars, Titan, and even the giant planets. We have Juno and Cassini recently have gone to Jupiter, taken gravimetric and magnetic measurements. But nonetheless, the amount of data is orders of magnitude less than what we have for the Earth. If you condense it, it's going to be megabytes or gigabytes. It's not going to be anywhere close to what we have for Earth. Similarly, for paleoclimates, we have proxy data. We have tree rings. We have isotope measurements from foraminifera at the bottom of the ocean bed deposits. We actually have some fossils which people have collected. We have carbon dioxide and ice cores and so on. So it's a fair amount of data. But again, it's not close to what we have for the present day. Again, it's going to be megabytes or gigabytes. And for exoplanets, planets outside of the solar system, there are 4,000 plus that we know of now. Almost certainly there are billions in our galaxy. Heather Knudsen, who's an observational astronomer at Caltech, said it's when we observe an exoplanet orbiting a star, it's like trying to observe two fireflies flying around each other in New York when you're watching them from Los Angeles. So it's really a much, much less data. It's pixels of observations. Perhaps there'll be more with JWST. If we regarded ourselves as physicists, then it's our job to try and understand these problems and how we're going to do that. What do we want to understand, say, for paleoclimate? Here's a well-known curve, sometimes called the Zakos curve, after my colleague here, Jim Zakos. And the main curve there, you see the temperature record from the early Eocene, about 50 million years ago. It's particularly warm, around about 50 million years ago, around about here. About on average 13 degrees Celsius warmer than it is today. And then over the past several million years ago, going through the Pliocene, times of human evolution, some million years ago, then into the ice ages, quite cool. Then in the Holocene, beginnings of so-called civilization, and now perhaps global warming again, which might, in an extreme scenario, take us up to the levels of the early Eocene in temperature. We'd like to understand that, but we're going to need to apply some physical principles to that. It's going to be hard to train a model, an AI model on that. So what can we do? And for light from an exoplanet, a planet orbits around its host sun, and we measure the light coming from the planet and the sun, and it produces a curve like this. These dots are observations. Oops, excuse me. And the dips are when the planet goes in front of the sun or behind the sun, and you see a reduction in the light. But oftentimes, this is pretty much all of the data you can get from an exoplanetary atmosphere. So clearly, what are we going to do? In a sense, we're going to have to go back to basic physical principles. So the problem is the climates, including the climates, of course, of exoplanets, not just Earth, they are truly complex systems. But compared to present-day Earth, as I've mentioned, paleoclimates and planetary climates are poorly observed. There's orders of magnitude less data for even nearby planets. So GCMs, a full-blown GCM for Earth, you have to tune it to get an appropriate answer. And of course, machine learning is a very good tool for tuning, but you have lots of data to tune it on. And you might try to, you can most likely tune a GCM to give you the light curve that we saw in the previous slide for some planet. You don't know whether you've tuned it correctly or not, and whether that tuning will apply to another planet. And as I mentioned, there are 4,000 known exoplanets. There might be 5,000 now. That number is changing almost on a weekly basis. So it's impossible to construct a separate model for each individual planet. Now, of course, there are billions of stars too. And we have models of stellar evolution, but planets are actually more varied than stars. Many stars follow what's known as a main sequence, and you get diagrams of luminosity versus temperature, which you can put a lot of stars on, but there's no such main sequence for planetary atmospheres. Whereas we would like to classify, come up with general principles, we can't use a one-size-fits-all approach for planetary atmospheres. So we can't just build complicated models. And there isn't really enough data to apply powerful machine learning methods currently. There may be in the future, perhaps. Partly because when you're coming up against a new situation, you need to extrapolate, if you will, rather than interpolate, because the data isn't there. So our motivations, as physicists, we want to understand what is going on. And even for Earth, I think it's important to understand, because suppose some phenomenon occurs in a particular model, like the Met Office GCM or the NCAR GCM, is that a robust response to some particular forcing? And if you change a parameter, because you have lots and lots of semi-empirical parameters in a model, if you change it and the behavior of the system changes because there's some a certain amount of structural instability in the model, then what do you do? So you tend to tune the model parameters, as a whole, so they work together well. But if you then pass into a non-Earth-like or even a past Earth-like regime, the observations are sparser. The model that you tune for the present day may not work so well. And of course, if a model, we still do have problems with the current day models. Some of them give a meteorologist will know what the ITCZ is, intertropical convergence zone. Models haven't always done well there, but how do you fix it? So what do? You have to apply physical principles, construct robust models, try to understand what's going on, and that's become well, what we do is we try and construct a hierarchy of models of Earth and planetary atmospheres. So models of varying degrees of complexity. At the high end, if you will, there would be a full GCM, an Earth system model. At the low end, there'd be some very simple model, which might just treat a planet as a point with solar radiation coming in, and radiation going out according to sigma t to the fourth. That would be a simple energy balance model, and you try to have a range of models all the way between. It's not rocket science in a sense that the basic physics is known. There's a little bit of an art in connecting all of these together. And there are many different types of hierarchies of models. On the left, taken a figure from a paper by Polvani et al. They've constructed a model using a hierarchy of models using the NCAR GCM. On the far left, here you see the actual Earth. The next one is a model of the Earth with continents and clouds and everything. Then there's a model which you take away the continents and you're looking at what an idealized Earth is. And then on the far right, an even simpler model with some other simple physics going on. And on the right, some of that ideas have been ensconced in this box model. Hierarchies of models go in different ways. On the horizontal, going back and forth here, there are different equations that you can use. There's different types of physics that you can put into a model, and so on. And the idea is, in a sense, that you try and simplify according to the system that you are looking at. So for Earth itself, you might indeed produce a complex model because you have the data for it. You really don't have that data for paleoclimate or for planetary climate. So it behooves you to actually try and construct a model with the appropriate complexity for, for the system that you are studying. So let's make this just a little bit more concrete and go back to my first example, which is paleoclimate. And here we have this rather well-known curve of temperature over the past 60 million years. And I'm going to focus on the early Eocene. So this region here, about 50 million years ago, it was Paleocene, Eocene thermal maximum. It was a very particularly warm period in Earth's past, about 10 to 15 degrees warmer on average than it is today. Most likely due to higher levels of CO2. And then, as I say, over the next several million years, the climate slowly cooled. prior to that, if we go back into deep time, we had some really rather wild on the figure on the left, some very wild fluctuations in Earth's climate. For example, there were periods when it was extremely cold, when it seems likely that the Earth was almost completely covered by ice, the so-called snowball Earth. And once it is covered by ice, then the ice is reflecting nearly all the solar radiation back into space, so it stays cold, and it's rather hard to break out of a snowball Earth. But I'm going to focus on this region here about 50 or so million years ago, and try to understand what's going on there. Now, the problem is not so much understanding the warmth itself. The warmth itself, the basic level of warmth is almost certainly due to high levels of carbon dioxide in the atmosphere, probably between 4 and 9 times the levels of carbon dioxide that we see now, perhaps up to 2,500 parts per million carbon dioxide. And we know that because of all the work that various paleoclimate people have done. For most recently, they've looked at boron isotopes in plankton or in plankton forams, and looking at the isotope concentration, you can tell what things like the seawater acidity were and the carbon dioxide levels were many million years ago, depending on where their location is at the sea bottom. This gives you some dating. And obviously there is quite a lot of uncertainty about it. And some people like to have a little joke that nothing changes faster than paleo data. But the field itself, the paleo field, does seem to have settled on the notion that levels of CO2 back in the early Eocene were about 4 to 9 or 4 to 10 times the levels of pre-industrial carbon dioxide. And that will give you quite a hefty increase in temperature, in global temperature. And when we look at time series, look at for example, the bottom two graphs. The middle one is carbon dioxide of the same time series. The bottom one is Delta 18, which is a proxy, is used as a proxy for temperature. And the levels of CO2 are certainly well correlated with the levels of temperature. So the basic idea, I think, is not controversial, that it's carbon dioxide levels which are increasing to very high levels. It's unlikely, I think, that we'll get to such high levels, in the near future. There aren't enough fossil fuels to burn, fortunately, to get to such high levels. Nonetheless, that's not so much of the problem that we are faced with. The problem more is that it appears that the meridional temperature gradient in those past climates was much less than it is today. I'm showing you here an early picture, data from some early work by Greenwood and Wing. There's been a lot more work done since then. But the picture remains that although the climate as a whole did warm, it warmed more at high latitudes than at low latitudes, quite considerably. And you can see that the gray shading is today's climate. And this graph at the top shows that at high latitudes, the temperature, or at least the surface temperature, was considerably warmer than it is today. And it turns out, although perhaps it's not so clear in this slide, that's especially true in winter. And there's very direct evidence for that. We don't need to look at, we don't need to do analysis of boron in planktons, which physicists like me find it hard to understand. We can actually just look at fossils. Fossil people have actually collected fossils from Ellesmere Island, for example, in North Canada. And in this paper by Eberle and Greenwood, they say that sediments in Canada's Arctic archipelago, so way up there, the latitude of northern Greenland, preserve evidence of a lush swamp forests of conifers such as redwoods and cedars, including the pine family, diverse flora with alder, birch, deciduous broadleaf trees. Very different from today. These swamps were inhabited at times by alligators, turtles, and fish, in addition to a diversity of mammals that included primates, tapirs, brontotheres, and hippo-like coryphodons, which coryphodons were the first large mammals to appear on Earth. Largely appeared after the dinosaur extinction. And the winter low temperatures at that time probably did not go below freezing, whereas today in North Canada Arctic, temperatures will get down to minus 40 degrees Celsius, so significantly warmer in winter over land. And I always like to show this picture, which is an artist's reconstruction of what the high Arctic rainforest was like back in the early Eocene. And this appeared in a serious scientific paper. But as a sort of a theoretical scientist working in physics, we don't ever get to put pictures like this in our papers. Well, I don't, anyway. My papers have line plots, and if I'm lucky, I have color contours or something like that. But here's the picture of this coryphodon 50 million years ago, way up in inside the Arctic Circle. So what's going on? So above freezing temperatures year-round, even at high CO2, it's hard to understand because the temperatures at low latitudes did not increase as much as that. They did increase, but not as much. And you would expect it to be cold, even when there's high levels of CO2, because there's no incoming solar radiation. It's still winter. Today, there's a relatively low heat capacity of the land because it's all ice covered. There's a low heat capacity that's going to give you cold winters. That's part of the key to how we can understand what is going on. So what we'd like to do is to obtain some credible year-round above freezing temperatures with reasonable levels of CO2. We can't just increase CO2 willy-nilly to very high levels, otherwise the planet itself gets too warm, and we don't satisfy the observations. So there's polar amplification. The warming is more in the poles, and there's reduced seasonality. How do we do that? Well, of course, one valid approach is to use a model for today, designed for today, an Earth system model. And you seek to model the climate with as much verisimilitude as possible. Downsides are that it's unavoidable use of many parameterizations. So what we've done, just as an alternative, not as a replacement, just as an alternative, is to use a somewhat simpler model, which we developed at the University of Exeter. It's a very flexible model it still solves the equations of motion, it still solves radiative transfer, but we don't try to have complicated parameterizations for clouds or so on. We're trying to understand what's going on. Now, so what's going on? What's wrong with big models, I guess? And a lot of comparative models have tried to do this, and here are two which apparently do quite well. The black vertical lines in the plot are observations with error bars, and the red and the green lines, one is the CESM, Community Earth System model, the other one is the GFDL model. Both run at 6 times CO2. And it seems that they actually compare fairly well on the annual average and are quite similar. But what is happening is that to some degree, they're getting the right answer through a bit of a cancellation of errors in the annual cycle. So the leftmost plot is the Arctic land temperature minimum. The right plot is the Arctic land temperature maximum. Various models going up to high levels of CO2. Not all models can go to such high levels of CO2 because they tend to break. The radiation code isn't good enough, and so they break. But what happens is that in winter, the models, especially this red model, the CESM, are too cold in winter, but too warm in summer. So they get the annual average right, but the cost is that they're, by plotting the annual average, they're sort of hiding some failures here. The difficult part is to get the seasonal cycle right. And because these models are rather complicated, it's hard to know exactly how you can get it right, or what are the key features enabling you to do that. Is a model getting it right or wrong because the cloud scheme is wrong, or the land surface model is wrong, or whatever. So let's take a much simpler model, and first thing we do is just increase the CO2 by a factor of 4, and then another factor of 4 to see what happens. This is using our rather simple model, ISCA. It's a simple GCM, in this instance with no clouds, no sea ice, present-day continents. We're just increasing the amount of CO2 and seeing what's happening. And so black line is present-day CO2 on the left plot. The red line is quadruple CO2. The blue line is 16 times current CO2. It warms, but what you can immediately see is that it actually warms larger, even in a simple model like this with no ice albedo feedback, no cloud variations. It's warming 10 degrees more on the annual mean at high latitudes than at low latitudes. What's doing that? And on the right-hand side, you can, the land is a solid line, and dashed lines are ocean. And not only is the warming greatest at high latitudes, but the warming is greatest over land rather than over ocean. And in a sense, that's what we're looking for the Eocene, because at high latitudes, the problem is warm relatively warm winters. So let me skip that one. And I'll skip that one too. Why should there be more warming where it is cold, and why should there be more warming over land than in the ocean? And you can understand that with an extremely simple model. Which is a model of, it's an energy balance model of the surface temperature. And so here's an equation. T sub S is the atmospheric, it's the surface temperature. C is its heat capacity. The things determining this variation in surface temperature, SW, the short wave radiation, the long wave radiation going out, some surface flux, and radiation going out, sigma T to the fourth. Now, it's a nonlinear equation because it's got this nonlinear term, sigma T to the fourth. Let's just linearize that to be A minus BT, where B is the linearization of sigma T to the fourth, 4 sigma T cubed. We warm an atmosphere by changing A. So we change the greenhouse effect. And how does the temperature change? Well, part of the effect is what is sometimes called the Planck feedback, that when B is small, so the base temperature is small, the temperature actually needs to change more in order to balance the greenhouse effect from the CO2. So if you warm something that's cold and you have a sigma T to the fourth response in the radiation, the increase in temperature will be greater where the temperature itself is smaller, just because of this rather simple nonlinear effect. And that's part of what is going on. The second effect is the heat capacity, C. Let's just put a seasonal cycle in here by letting A vary with a cosine of omega T. And then we can actually solve this equation. It's basically a simple harmonic oscillator. So the solution is this guy, A0, C squared omega squared plus B squared to the 1.5 on the bottom. The amplitude of this seasonal cycle then has these two effects: the base temperature B, which I mentioned before, and the heat capacity C. So warmer climates have smaller annual cycles, and if you increase the heat capacity of the land surface, you'll get a smaller annual cycle. And of course, why should the heat capacity be larger in the Eocene climates? The reason is that it's sufficiently warm that the ice has gone away. When you have ice cover, you'll get a very small heat capacity. And when you, as soon as all that ice melts, you've got a soaking land surface, you've got lakes, you've got forests, a much higher heat capacity. And so you're going to get a smaller seasonal cycle. So that also works in your favor. So to cut a long story short, we then explored the effects of these models, of these changes in parameters in a GCM, and found that if we increased our land heat capacity over land, then we could, with a little bit of tweaking, but not excessively tweaking, obtain a seasonal cycle which was in the bounds of the proxy observations. And one conclusion here is that, in a sense, the solution is coming from known physics. There's nothing too difficult about this. We're increasing the land heat capacity. The Planck feedback is built into the model. We do have to get finally over the line, we do have to increase cloudiness in some ways, but that's not the primary effect. It's really just this Planck feedback and the land heat capacity. And furthermore, we said the pole to equator temperature gradient was much decreased in the Eocene, which has led people to postulate completely different changes in the atmospheric general circulation. For example, a Hadley cell going all the way to the pole. In fact, we think that's not correct. It's only the surface temperature gradient which has actually changed. It's not the temperature gradient in the middle of the atmosphere. It's just the surface change because of the lapse rate has changed at high latitudes. So, conclusions for this part of the talk is that how do you get warm, non-freezing winters over land? The third part here. And there's three parts to it. Polar amplification, because of this Planck feedback and the lapse rate changes. It's a weaker seasonal cycle than today. And finally, we did have to invoke some cloud effects to actually get us over the line and to get simulations which were truly in accord. So the precise combination is hard to discern of what does get it right. But getting seasonal and geographic, more data about the seasonal and geographic variations is the key, or will be the key to finally understanding this. But no true new physics is needed. Let me just briefly talk about then a problem with exoplanets for the last 5 or 10 minutes. It's a similar kind of problem, but in spades, in the sense that we have even less data, especially for exoplanets, and a lot of the observations of exoplanets, the data has come from the so-called transiting method, that a planet passes in front of its sun and behind the sun, and you can see this schematic here, that the sun is the star, the planet is going around it. We are billions of miles away from it. But we're able to, almost magically, evaluate how much radiation is coming from this sun-star combination. And this data is known as phase curves, and here are two examples. One of a hot Jupiter and a giant planet orbiting its sun, and here a so-called super Earth. Just look at the bottom one, that's for clarity, and you can see the first big dip is where the planet goes in front of the star, and the planet goes in front of the star, the amount of radiation from the star is diminished by a very small amount, which amazingly enough we can measure. And when the planet goes behind the star, the radiation also diminishes because you're not getting any radiation from the planet itself, because the planet is behind the star. And that gives you, it's more or less, total radiation is more or less constant, especially if you take out these big dips, but it's not quite constant. And why is it not quite constant? You see, it's when the planet is about to go behind the star. So if you look at the inset at the bottom left, the total amount of radiation is actually at a maximum just before it goes behind the star. So it's a maximum here. And it goes behind the star, but it keeps on diminishing. And it's the amount of radiation when the planet is in front of the star, the amount of total radiation when the planet is in front of the star is actually less than when the planet is going behind the star. And why is that? Well, the reason that the interpretation of this is to do with where the hotspot of the star, of the planet is. So you might expect, here's the star again. It's blasting the planet. The planet, you'd expect the planet to be hottest at the substellar point, directly underneath the sun. Now, but these graphs suggest that it's not. They suggest that the hotspot is actually offset from the substellar point, and it's offset from the substellar point because of the atmospheric circulation. So the planet's tidally locked. It means that the actual rotation rate of the planet is the same as that as the orbital rate. So it's got the same side pointing towards the sun. But if the hotspot is slightly offset, so slightly downstream of the substellar point, so here, look at where the hotspot is. So just before the planet goes behind the sun, the hotspot is pointing towards us. And so that will give us the most radiation. When the planet emerges from the sun, at the top left one, the hotspot is pointing away from us. You know, we're down at the bottom of the screen, so we're going to get less radiation. So the interpretation of that is that the hotspot is offset from the substellar point because the planet is super-rotating, i.e. it's going faster at the equator than the planet itself. So it's advecting the hotspot around in that direction. So, and that seems to be a fairly common, but not quite universal feature of tidally locked planets. And of course, other planets super rotate too, in particular slow rotators, like Venus and Titan. So I'd like to understand the mechanisms of superrotation. Why is it surprising? It's surprising because angular momentum is conserved. So if you imagine taking a ring of air from the equator and moving it polewards, it'll conserve its angular momentum. So as it moves polewards, it will actually spin faster than the Earth. But by the same token, if we move a ring of air from a high latitude towards the equator, it will still conserve its angular momentum, it will subrotate. So by and large, we would expect subrotation at the equator because air coming in from high latitudes will subrotate by conservation of angular momentum. So something else has to happen. And what actually happens is that we have eddies. And if the eddies have this shape, if there's zonal asymmetry, we will get superrotation. So the trick is to produce eddies which look like this. And as I mentioned, as well as exoplanets superrotating, slowly rotating planets also superrotate. This is a plot of Venus. And Venus is super-rotating at about 100 meters per second. So it's spinning around really quickly. Venus is a very slow rotator. Its sidereal day is about 200 days, 200 Earth days. So it's rotating very slowly, but it nevertheless super-rotates. So back to tidally locked planets, how do we produce superrotation? Well, we produce it because of something which has been known for quite some time in terms of Earth's atmosphere. But if we have some heating which is concentrated in a particular spot, the substellar point in an exoplanet, it produces a characteristic shape like this, which is known as the Matsuno-Gill pattern to terrestrial Earth scientists. Produces this shape because it produces Kelvin waves at the equator, produces Rossby waves off the equator. They produce this rather characteristic banana-shaped pattern, and it converges momentum towards the equator. So just by the nature of so let's summarize there's a substellar point heating at a particular point at the equator in a tidally locked planet. The response to that is actually this gill pattern when you solve the equations. And this gill pattern has this banana-like shape, and it converges momentum towards the equator, which then super-rotates, which then moves the hotspot actually downstream. And the same thing seems to happen in slow rotators. But in slow rotators, there's no hotspot. Now, here's just a plot of some simulations that we did, just with a very simple atmospheric model, making this rotation. Just look at the bottom row. This is Earth's rotation, rotation by 5, rotation by 20, rotation by cut down by a factor of 100 like Venus. And the red color contours mark the amount of superrotation that we're getting, the amount of eastward flow at the equator. So how is that doing it? It's doing it in a slightly different way. The basic state that the forcing is producing is perfectly zonally symmetric. No superrotation there, but it produces a large shear, a large horizontal shear in the flow. And that shear itself turns out to be unstable. And the instability is actually producing this banana-shaped pattern. So it's not quite the same as a tidally locked planet, but the essential mechanism is rather similar, that it's producing these banana-shaped eddies. So the key result there is, I guess, that you need eddies to drive superrotation. You get a very similar patterns in a slow rotator as in a tidally locked simulation. The mechanisms of producing this are somewhat different, but perhaps the underlying mechanism we can say is the same in that they produce these V-shaped eddies. So I'll perhaps stop there and just give you some sort of grand conclusions that understanding Earth's climate and present near future climate has reached a somewhat mature stage. We're now looking to understand the details. The details are extremely important. And the comprehensive models have been very successful for weather and also for climate. Almost certainly machine learning is going to play an important role in that. Paleoclimate and planetary climate perhaps aren't ready for that at the moment, or not ready in the same way, because there's a lot less data for it, and the lowest order problems are still important. The same physical principles, so I think it really is a happy hunting ground for physicists who are looking for basic problems in climate dynamics. And I'll stop there. Thank you for listening.
Okay, great. Thank you very much for the fascinating talk, Jeff. So there's already one question by AD Zhang in the Q&A. Probably you can see the question, right? And if you just answer that. And for others, if you have questions, please just type that into the Q&A feature. You can also raise your hand if you want to.
Okay.
Just speak and ask the question.
Q&A, there we go. CO2 level decreases from the Eocene. Most likely it's volcanism, or the lack of, to do with the weathering. So it's really a question for a geomorphologist. But the levels of CO2 in the atmosphere are not on these very long timescales. Million-year timescales are determined largely by volcanic effects. Volcanism can put CO2 into the atmosphere. Weathering can take it out of the atmosphere, and you get into an equilibrium. But if there is some excessive volcanism for tectonic reasons, you'll get much larger CO2 levels. On shorter timescales, and by short I mean sort of 50,000-year timescales, 100,000-year timescales, the ocean circulation will actually play a large role. So if you look at things like the last ice age, when CO2 was down to about 190 parts per million, perhaps much less than it is now, that was most likely due to uptake by the ocean. But on these long time scales, it's very hard to, it's hard for the ocean to be so important, and it's more likely that volcanism is. Paula, Jesse, what would a mechanism for changed heat capacity of land be? Hi, Paula. It's because the land is not covered with ice and with permafrost. At high latitudes, I don't think the heat capacity will change much at low latitudes where it's already not freezing, but at high latitudes, once it stops freezing, the land is at high latitudes, north of Canada, you will often have ice cover or permafrost, which tends to be very poor at absorbing heat, so the heat capacity is small. But once that is all melted, you have forests, and you have swamps and lakes, which the paleoclimatologists tell me was fairly common. They will have a heat capacity which is quite a few times larger. Rick Mifflin, how do you validate your cloud water vapor models at high? Well, that's the key thing. By and large, they're not validated, and that's why there is a problem that if you rely on cloud feedbacks to give you the bulk of the changes, you're on rather shaky ground. A distinguished colleague of mine, who shall be nameless for this talk, said invoking cloud feedbacks to explain something like this is the last refuge of the scoundrel, because you can't really validate them. I mean, what you can do, and people are doing and will do, is to actually make very explicit models of clouds. Almost direct numerical simulations of clouds, which have detailed aerosols and detailed microphysics based on physical principles. And the idea would be that if you are doing a DNS of a cloud, that will become your ground truth. And then you would validate your parameterized cloud model against these ground truth models. And that's, to some degree, the way forward for a lot of parameterizations which we have in GCMs. It's one of the ways forward for convective parameterizations is that you actually build a DNS model, direct numerical simulation, or an LAS model, large eddy simulation, which simulates convection explicitly, and so it's not being parameterized, so it should work at all CO2 levels. But therein lies the problem. That's something that has to be done. I think, and it's the way forward. Elizabeth produced a simple. This is from Francesco Paparella. Hi, Francesco. Published a simple box model of equitable climate centered on cloud feedbacks. You made a case that energy Planck feedback is what produces an equitable climate. I don't think that they're contradicting each other, Francesco. I'm just arguing that Planck feedback is part of what is going on. I think the three things which are going on, I'm sorry if I didn't make this clear, is Planck feedback is one effect. The second thing is a larger heat capacity, which reduces the surface, which reduces the amplitude of the seasonal cycle, and the third may well be cloud feedbacks. So I think it does seem likely that cloud feedbacks will be important in as it were, getting us over the line. And there are good arguments for that Ellie and Dorian Abbott made. The cloud feedbacks will be more important. That you can, for example, get more convection at high latitudes in these Eocene climates. More convection will give you more high clouds, which give you an enhanced greenhouse effect, which give you more warming. So I'm not arguing that cloud feedbacks aren't important. I'm just making the point that some other feedbacks that are perhaps less controversial than cloud feedbacks play an important role. John Retlifer, John. A stochastic version of your linearized DBM can lead to qualitatively very different results depending on the nature and amplitude of the noise and whether it's additive or multiplicative. Yeah, I guess that's a comment. Haven't done that. I can in part believe you, but I also think that some of these processes, which I did mention, will still hold, but it's something to be done. More research is needed, etc. Anonymous attendee, hello, Anonymous. For small time scale, less than 5,000 years, the ocean plays a big role. Yep. What should we do what should we focus on improving our ocean models, and does that matter for climate? Yeah, for sure it does. Similar to the atmosphere, resolution always plays a big role. We need to seek to improve our resolution. We also need to seek to improve our parameterizations of things like mixing, dipycnal mixing in the ocean. Dipycnal mixing and things like that do play a rather large role in the overturning circulation of the ocean. For example, if we are looking at the meridional overturning circulation, which is one of the key components of climate, although a lot of it is driven in part by winds in the ACC, which give us upwelling. It's emerged over the last decade or so, I think, that in fact mixing can play a fairly large role, and that you can get upwelling. You can get diabatic upwelling or dipycnal upwelling in the Pacific, which in part drives the overturning circulation in the Atlantic. So I don't know whether we have good understanding of what that is doing. And also, even as we increase our resolution, things like there will always be processes which we are not resolving. That's, unavoidable. We're not ever going to get down to the Kolmogorov scale. And so even though these days in modern models, we're more or less decently resolving mesoscale eddies, even for climate purposes, we're not resolving the smaller scale eddies, the submesoscale eddies. So, so there are roles there, both for physical understanding, and I'm sure AI will play a role there in that. So, yeah, lots of effort towards the ocean as well as the atmosphere. Abu, do you think a warmer future climate of the Earth could be super-rotating? I'm thinking of Venus with its high CO2 levels and trying to think about the Earth. Yeah. Interesting question, although I don't know whether Venus is a good analog. Venus, not only does it have high CO2 levels, it's pretty much its entire atmosphere is CO2. So it's vastly higher CO2 and not going to get there. And it's also rotating much, much more slowly. Its sidereal day is something like 240 Earth days, so very slowly rotating. But having said that, some simulations using general circulation models have given a super-rotating Earth, and there are also arguments which say that once we get into a super-rotating state, we'll stay into a super-rotating state because there'll be hysteresis effects. To some degree, I think Earth and Mars are almost on the verge of super-rotating. They're marginally super-rotating. I wouldn't like to say, I think, as to whether Earth will get into one I think that's probably a quantitative question. And that's the kind of question that we probably do need a high-end comprehensive model, a trustworthy high-end comprehensive model to answer. So.
Okay, great. Well, thank you very much, Jeff, for a fantastic talk. And you got a lot of questions, and thanks for the answers. So the talk was recorded, so the recording will be posted. And again, we really appreciate the talk. Thank you, everyone. We are not going to have any seminar in December, but Alex Robel is going to talk about ice sheets in January. Thank you very much, and see you later.
Okay, thanks, everyone.
Thanks, Jeff.